In previous sections, we discussed the sample mean as an estimation of the population mean. That estimation depends on the sample size. The larger the sample size, the closer to the population mean. But it also depends on the standard deviation of the sample. In this chapter, we will discuss how far off the true value is likely to be. A confidence interval will give us the likelihood that the true value is in between an interval around the sample mean. The objectives of these lessons are to define confidence intervals, to calculate intervals with two-side and one-side confidence levels, and to calculate the required sample size to meet the specified confidence level. An estimate of the population mean, the sample mean, is a point estimate. These estimates are almost never exactly equal to the true values because they are single points. In order for the point estimate to be useful, it is necessary to describe just how far off from the true value it is likely to be. To describe how far is our estimate from the true value, the uncertainty must be reported. So it's customary to write our value plus or minus the uncertainty. And this uncertainty, it will be described in terms of the standard deviation. Let's review the characteristics of the normal distributed variable. For any normal distribution, the probability that a randomly chosen variable is in between a range can be expressed in terms of the mean and the standard deviation sigma. The probability that a random choose value is in the range defined by mu minus sigma and mu plus sigma is approximately equal to 68% no matter mu or sigma. In the same way, the probability that randomly choose variable is in between mu minus 2 sigma and mu plus 2 sigma is this area that corresponds to approximately 95%. And if we increase the range to mu minus 3 sigma to mu plus 3 sigma, the probability that the randomly chosen value is in this range is equal to 99.7%. So we can use mu and sigma to describe a range of probabilities. Let's illustrate the concept of confidence interval. Let's suppose that we have a diameter and we are measuring the diameter, and the variable is normally distributed. And after doing some computation, so we conclude that the mean is 14 centimeters and the uncertainty is 0.1 centimeters. So we can describe that the diameter is equal to 14 plus or minus 0.1 centimeters. So this will give us a range of 13.9 to 14.1, and because this is plus or minus 1 standard deviation, so we can conclude that we are 68% confident that the true value is between this interval. In the same way, if we decide to choose instead of 1 sigma 2 sigma, so we can describe the interval x plus or minus 3 sigma, which will correspond to 13.7 to 14.3, and now we can say that we are 99.7% confident that the true value is between this interval. Assume that we have a large sample and we want to compute the confidence interval. Recall from the previous example that the population mean will not be exactly equal to the sample mean. So assuming that this is the distribution of the population, so this point will be the population mean, and the sample mean will be located somewhere next to the population mean. And the confidence interval that we want to select is an interval which is actually covering the population mean. We want the population mean to be inside the interval. How do we construct the interval given that we don't know the true value of the mean? Well, let's consider that we have a large sample, x1 to xn, and mu and sigma are the mean and standard deviation of the population. Now, if x is the mean of the large sample, so we can use the central limit theorem, and we know that the mean is normally distributed, so the mean is normally distributed with mean mu and standard deviation given by sigma of x bar, the standard deviation of the mean. Now, this standard deviation of the mean is equal to the standard deviation of the population divided by the square root of n, where n is the size of the sample. Now, since sigma x is unknown, we can approximate sigma x with the standard deviation of the sample. Now, to construct a confidence interval of b percentage, whatever b number is, we need to find out the confidence interval given by x bar plus or minus a times sigma x bar. So, in other words, given b, we need to find a. Recall that the area under the distribution function is equal to 1. So we can divide this area in 3 regions. Let me do it in the next slide. So the first region is the one on the left. The second region is our desired confidence fraction. And the third one is the last region. So we are going to call this alpha over 2, and that should be equal to this alpha over 2 because our interval is symmetric along x bar. So the region in between is 1 minus alpha. So the whole area is equal to 1. So this is equal to b in our last slide. Now this is convenient because on the tables of a cumulative distribution function, we found the values for the left-hand side regions, for the integral from minus infinity to x minus a sigma x bar. Assume that the desired confidence interval fraction is equal to 1 minus alpha. For example, let's say that we are interested in a 95% interval of confidence. So that means that 1 minus alpha is equal to 0.95, right? And alpha will be equal to 0.05, and alpha over 2 will be equal to 0.025. So we will be looking on the tables to this value. To find our interval, we need to relate our distribution function, our normal distribution function, to a standard normal distribution function with mu equal to 0 and sigma equal to 1, which is the one that are in the book. For that, we need to convert our x variable into z variable So this will be the equivalent of C of alpha over 2, which corresponds to x minus a times sigma of x bar, and the complementary value, which is a of alpha over 2, let me put it here, complementary, because the mean is 0, that will be the negative of the other one. So the definition of z of alpha over 2 is equal to x minus x bar divided by sigma of x bar. So recall that the value that we are interested, x, this will be our value that corresponds to c over alpha 2. So x in reality, let me put it here, x is equal to x bar minus a times sigma of x bar. So if we solve for x, what we have is that z of alpha over 2 multiplied by sigma of x bar is equal to x minus x bar. But recall that x is equal to x bar minus a times sigma of x bar, this minus x bar. So the x bar will cancel with the x bar, and then we have that z of alpha over 2 multiplied by sigma of x bar is equal to a multiplied by sigma of x bar. So sigma of x bar is the same, so that means that a is equal to z of alpha over 2. So this is an important result. So that's going to be the one that we are going to look in the table. In this particular example, we go into the table looking for 0.025, table A2. So we have the value of 0.025. So we look for the corresponding values, and so we can conclude that C is equal to minus 1.96. So this corresponds to z of alpha over 2 equal to minus 1.96. So our interval of confidence will be equal to x bar plus or minus 1.96 sigma of x bar. Let's illustrate now with an example that shows the actual population mean. So in this example, we have this population mean located at this point, and we are going to define a 95% interval of confidence. Now the interval of confidence is for the sample mean. So we have the sample mean, and the interval of confidence is this one highlighted in yellow. So in the left hand side, okay, by the way, when we compute, we find a value of a of 1.96 for an interval of confidence of 95%. Now in this particular case, we can see that the mean is inside the interval of confidence, so we're good. But it could be cases like in the right hand side. So we have the same size for the interval of confidence, but in this case the mean is far away and the interval of confidence doesn't actually contain the mean. In this case, we are not capturing the mean inside the confidence interval. Okay, in the left hand side, we say that we see that X lies within the middle 95 of the population distribution, while in this unusual case X lies outside of the 95% of the population distribution, and therefore it fails to cover the true population mean. Let's summarize what we found so far. So we need to define a confidence interval for a given fraction, so the 1 minus alpha fraction, that I also call it B, and the confidence interval is defined by x mean plus or minus z over alpha 2 multiplied by sigma of x mean. So that's the standard deviation of x bar. Now we do this because we know that the means are normally distributed with a mean mu and standard deviation sigma of x bar, and sigma of x bar is equal to the sample standard deviation divided by the square root of n, and this is for a large sample size, corresponds a large sample size. Now on the left hand side we can see different typical values for different intervals of confidence. So remember, when we take z of alpha over 2 equal to 1, we get a 68% of confidence interval. 1.64 corresponds to 90%, 1.96 corresponds to 95%, and so forth. The last one is 3 times the standard deviation of the sample mean, will corresponds to 99.7 confidence interval for mu.